I'm not trying to get into very specific areas. I'm trying to give a general idea. That's why it's called general mill processing. And it does not address tube, pipe, or castings or anything like that. This is for sheet and strip, which in many cases people mean when they talk about mill processing. And since the upcoming tour is of Revere, they do sheet and strip. So here we are. Well, all right, I had trouble moving the cursor for a moment. I'll talk about a little introduction about casting. You always have to cast the metal, rolling, both hot and cold, finishing, packaging, and some common alloys that are produced. Now, I've shown this screen on many occasions. I find it interesting. This is ancient mill processing or processing of metals. Essentially, you have a series of drawings here, a pictograph, if you will, from Egyptian and Grecian times, showing what was done at that time to melt and cast metal into various little ingots and pots. And you'll note the safety equipment was very advanced. Anyway, these come off of various paintings and drawings from that time. Well, in wrought products, the definitions of flat products, I'd like to go over a few. Plate. Plate is a rolled flat product over 0.188 inches thick and generally over 12 inches wide. Other people, this is the accepted definition. Now people can define it different ways at different times. Sheet is a rolled flat product that varies in thickness up to 0.188 and is over 20 inches wide generally. So there's some overlap. Strip is a rolled flat product that varies in width up to and includes 20 inches wide with a slit, sheared, or sawed edges. These are general definitions. Each company and each facility may have slightly different definitions, but these are used to be CDA definitions and now they're ASTM. Well, I'd like to go through some general diagram of copper production and recycling. You start with the mine, but in that particular box where all the red squares are, you end up with concentrates and matte and scrap that comes back. That's in the bottom tier in the green boxes. They all go into a smelter. Now, a smelter means that you're taking sulfur out of the ore. About 67% of the ore, copper ore, is sulfur bearing. The other is oxide or tied up in oxides. So an oxidic ore doesn't have to go through a smelter. It can go straight through what the box called SX or EW, electrowin or solvent extraction. That's a little different path. But the smelter takes the sulfur out, then you take the oxide out, then you go to the refinery, and essentially after all these points, you end up with refined copper. Refined copper then goes into a variety of applications. They're all in yellow. You go to a wire rod plant or a wire mill. You go to a brass mill or a copper mill. You go to a foundry. Other plants like tube, sheet, strip, or specialty casting and drawing operations. Some of them make shapes directly. And these semis or semi-finished products are then sent on to the orange boxes where they're put into construction, electrical and electronic equipment, and various other consumer and manufactured goods areas. All these equipment and items with copper in it then go to finished products, and then the dark red boxes here are product in use or lifetime use. This is wire in your house. This is circuit breakers. This is tube for water in your house. This is sheet for your roof. This is wiring in your car. This is electrical and electronic things that are in your phone and so forth. Eventually, the product use is used up or is considered to be used up. You have another box here, abandoned, stored, reused, end-of-life products. End-of-life products go over to the end-of-life management area in yellow, and all those are acronyms for ways to take the metal out and redo it into new material. And you'll note that there are end-of-life products boxes, and you can go back and forth and around with this diagram. This diagram was developed by the International Copper Study Group and shows a general overall picture of what happens to copper and points out that it is highly recyclable. What happens in the mill? We transform various materials, scrap, pure metals, and additives into semi-finished products for industrial use. There are several steps in the processing of this material. The final product, which is defined by the alloy, the size, and the shape of the product, is dictated by the customer's order. So when Revere gets, or any mill for that matter, gets an order, it's for 032 half hard strip that's 1 inch wide, slit in 1 inch wide coils, and the coils are a certain size and they're packed a certain way. All this is in the customer specification. Well, I have some stylized renderings of processing. Here's a processing flow, which is the hot end. You have a ladle and a tundish and a casting line, and your direct casting, this is direct continuous casting of sheet. It goes through a variety of pinch rolls and hot rolling mills and water cooling, and then it's upcoiled. Not everybody, in fact, very few in the copper industry do direct casting like this. Most of the mills do something more akin to this stylized flow. You have material that comes in, and scrap, raw materials of various types, and so forth. And that is from the hot end. You have what's called big size strip. Big size strip is hot band, or material that's like 3/8 inch thick. But it's still like 37, 38 inches wide. You go through various rolling stages. You get sheet that's now 032, 010 or something like that. it can be annealed at various stages to produce a variety of tempers. Middle-sized strip, and by middle-sized strip, this illustration means narrower. So it's been slit into, say, a foot wide. The edges have been trimmed. Then you have small-sized strip. It can be down to the final 1 inch wide or something like that. There may be a final heat treatment or a cleaning. Goes to packing and then transport. Sent to the customer. The casting. Well, there's two types of furnaces that are used generally in the copper industry. One more than the other these days. In the reverberatory furnace, it's a large metal pool of molten metal. It can be like almost 100,000 pounds. These are for large volume alloys. Content in them, mostly coppers. Long continuous casting runs are needed when you have this much metal. However, electric arc furnaces, because of controls and availability, are more popular than ever as we are presently and moving forward. They're smaller volumes, but they come in different sizes. The alloy content is generally higher. Brasses, bronzes, copper nickels, and so forth are melted in these type furnaces. Specific production characteristics. And it's enclosed. It's completely enclosed. Anything that comes out of here is collected. More favored these days than ever. So just for illustration purposes, here's a reverberatory furnace. Here is the pool of metal, molten metal. And the fire comes out of, or the heat comes out of E, and you exhaust out of G, and you have a lot more trouble in environmental characteristics with this furnace than with anything else. But like I said, it can be used very effectively for like alloy 110, alloy 120, 122, and some of the 100 series coppers. But an electric arc furnace, and this is only one illustration, drops over this and fully seals it. It looks like a cooking pot with a sealed lid, a pressure cooker. Only it has a stack or a vent on the top that any effluent and or gases come on off of it, go up into a bag house and are collected. There's a natural circulation here. Well, what do you put in these furnaces? Well, like we said earlier, you put a variety of materials. Furnace charge includes both virgin metals and scrap. Now, virgin metals are substantially pure metals from refineries and or other areas. You have electrolytic copper, cathode, ingot, or bar. You have slab zinc or slab tin or nickel balls or phosphorus in usually tied up in a master alloy, and other pure metal additions. People have been putting manganese in. There's a little bit of few alloys with silicon, with manganese, magnesium. So there's many things that can be added. Many of these other metal additions are made by master alloys. And it's easier to get it in if somebody else has already made an alloy, maybe highly concentrated, with that other metal addition added. So you just drop it in. It's like dropping pellets into something, and they gradually melt, and then you assay the furnace afterwards. Scrap is a very important component, however, and that's why I brought up the recyclability. Scrap can be in several forms. You have runaround scrap, you have customer scrap, and you have scrap from merchants. Okay, runaround scrap is primarily from inside your mill. You have side trimmings, end trimmings, cuttings here and there, and all that material can be recaptured, sent back to the melt shop. Customer scrap, once you send the sheet, strip, or plate out, they make something out of it and don't use all of it. All those trimmings and cuttings and so forth, if they're put in a barrel or in a bin and identified and returned, they are of known composition. They can be easily put back through the melt shop and combined into a furnace charge. That's very good practice. Scrap merchants. Scrap recycling people work all the time gathering up copper wire from various jobs in various locations. When that's all 110 copper, very pure copper, generally, they have cuttings from roofing sheet or chimney flashings or various other things. They have small parts that they find all over the place, or somebody's recycling brass faucets or brass this or that from their home. That's from a scrap merchant. They sort it and they sell it back to the mill. So all of these can be reused and recycled very successfully. Well, let's go through just general casting methods. You have continuous casting, which I illustrated earlier. Very few mills use that. It requires a very large quantity of ongoing orders in one or a few alloys to do that. Then you have semi-continuous casting, which is, as will be illustrated in a little bit, a short continuous cast, but it's stopped. So you can manage the product better. And it's more akin to what is normally done in the copper industry. And then horizontal casting. Horizontal casting is used for specialty alloys that require a long melting or long solidification zone, usually. Horizontal casting many times is used for copper nickel alloys if they're cast this way, or for complex alloy compositions that someone wants to cast in a sheet strip form. Well, here's a continuous casting schematic. This could be steel. This could be copper. This could be aluminum. Could be anything. I've seen it in, more specifically, in steel and copper. Many times the upper mold discharge rack before it turns horizontal is longer. The solidification zone is in that area just below the mold, and it may need longer solidification time. But in any event, you come down to, as the metal is still warm and still formable, into a horizontal feed, outfeed, or takeout, and a straightener to make sure that everything is straight. It's fed out onto a table or a run-out area, and in many cases, this is cut to length. This is semi-continuous casting. Again, a schematic. You have charging schematically shown where you put metal into charge buckets. You have feeds. You have melting furnaces. Here they show 5 melting furnaces, which generally is not the case, but it can be multiple melting furnaces. You have a holding furnace, or maybe you just have one pouring furnace. In the case of electric arc furnaces, many times they are articulated and they pour directly from an electric arc furnace into these water-cooled molds, and the slabs and rams at the bottom in the and this is usually in the floor of the mill, and this is your cooling zone, and the rams, or the holding, the bottom holding items, move down vertically until the slab is complete. Then the pour is done. The melt pour from the furnace is stopped. Everything is complete. Well, most people would call these slabs, and they are in this illustration, but in copper we call it cake. Go figure, there's a historical reason for that. Anyway, these slabs or cakes are then taken out, and here's a more detailed look at what happens in a vertical slab casting. You have the solid ingot, you have the liquid metal, and you have the water sprays at the top where it's solidifying. You have the platform, and it's coming down into the pit. You then, after things are done, you grab it at the top and you pull it out of the pit. So you have to have a lot of head clearance above. Here's a closer look at the cooling zone. Well, then we go on to horizontal continuous casting. You have a charge bucket, which has all the alloy ingredients and so forth. And you have the melting furnace, which is where you finalize the composition. And then you pour out of there into the horizontal casting furnace. And you'll note you're casting out of the bottom of that casting furnace. Any bad stuff in this melt will float to the top. It is skimmed. Any oxides that develop will be on the top. You don't want that in many of these materials. And these are highly alloyed usually. The casting is slow. It's high cost and high value material. Well, let's go on to hot rolling. This is what you do immediately after, or generally after, in the normal flow of operations after you cast something. The purpose of hot rolling is to get the cast metal, which is usually, well, it can be between 5 and 7 inches thick. In some cases it can be thinner, but usually it's thicker in producing a slab or a cake. And the slabs or cakes are cut into shorter lengths. for ease of processing generally. You want to roll this down to about a 3/8 to 5/8 inch thickness, usually 3/8, for feed into the cold rolling section of the mill. Hot rolling allows much faster reductions because the metal's microstructure is weakened by the higher temperatures. You extract the cake out of the furnace and it's red hot, sometimes bordering on white hot. The structure, crystalline structure, is weakened because of the heat, and it allows faster reductions with no microstructural change per se. Although you do have microstructural change, but it's continuous, and generally you do an odd number of passes in the hot end, 7, 9, or 11, or something like that, and then coil it up, and it forms an oxide, dark black oxide. Well, this is what happens in the hot rolling interactions. You have unworked crystals, which are very large, very easily formed when it was cast. The rolls, and usually it's a 4-high reversing mill that is used for the hot rolling to break things down, and the crystals reform. But you're doing multiple passes, so you end up with multiple recrystallizations as you get thinner. So you end up with about 3/8 inch thick. Other hot end equipment, you have surface conditioning. You can have surface millers or surface grinders. And obviously you have upcoilers for hot band, easier to handle. But it's very important in the surface conditioning aspect to get all that oxide that is formed off before you roll into the cold end. If you roll oxide into the surface, you're really in trouble. So you want to get all that material off. Well, then we move on to cold rolling. Purpose of cold rolling is to provide a final size and shape, to develop a proper or final temper, to develop good surface quality. Whereas the hot band was very kind of rough, and especially after it was ground on the surface to get the oxides off. What you're trying to do is you're cleaning up your act here. You're going from 3/8 inch thick approximately down to 0.010, say, for example. That's a huge reduction. Now you've already taken the hot band from like 6 inches thick down to 3/8. Here you're taking it in more controlled ways down to a final size, 010, 032, something like that. So you have several functions in cold rolling. You have breakdown rolling, which is getting it from 3/8 down to close to what you're planning to do. You have intermediate rolling, and many times intermediate rolling is done after, and many of the coils that are processed here are between 36 and 38 inches, maybe 39 inches wide. During breakdown rolling, you allow the edges to mush out, so to speak, and eventually you trim that. That's runaround scrap. In intermediate rolling, some of that is still done. You get rid of those edge defects. But once you get down to finish rolling, you're pretty much at final gauge, maybe not width. or very close to final gauge. Now there's several types of rolling mills, and here's 4. You have a 2-high rolling mill, which is hardly ever used these days. A 4-high rolling mill is something I told you was used in the hot end to do the breakdown rolling. And those are usually reversing mills. Then you have 2, and a lot of you can have a 6-high, which is not illustrated here. It has 2 backup or support rolls supporting the work roll. There are a number of those. More common to get good shape and surface quality these days are cluster mills. Illustration C in the lower left, you have 1, 2, and 3 levels of cluster mills. That's, many people call them a Zentzumer mill or a Z mill. It was developed by a gentleman named Zentzumer. And then planetary rolling mills, which in the copper industry are not very well used. But I show it for illustration purposes. Here's a cluster mill, sort of an exploded view, ghostly view of what it looks like inside. It's usually all enclosed. Well, once you're rolling, many times the strip sheet product has to be annealed or softened so that you can continue to process it. Now, as you're rolling the metal, it's getting harder, stronger. When you talk about hardness of the metal, it indicates that the metal has become stronger. As the metal becomes stronger, it pushes it back against the rolling mills. It makes it harder for the mill to roll it down. It's a normal, standard reaction of the metal. So you have to go to annealing. And annealing relaxes the metal so you can process it further. Purpose of annealing, provide relaxation to the grain structure. As you roll down further and further, especially in the cold end, you get smaller and smaller grains or crystals of the metal, and they get stronger and stronger, and you have to relax that. Allow further processing of the metal. If you don't do this, many times you can't get to the temper you want to or the size you want to because the metal has gotten strong enough that it resists rolling. And you may want to develop a final temper, and a dead soft temper is produced in the annealing furnaces. I always use the analogy of annealing as being where you and I, or anyone, has a weekend off and we go to the beach and relax, and the warmth of the sun relaxes you and takes all your stresses out. Well, that's the warmth of the furnace. It takes the stresses out, but it has to be, the metal has to be in there a certain period of time before all the stress is relieved. Well, there's 2 types of annealing. Everything's complicated. Bell annealing, and here you see a gentleman loading a whole series of coils of various thicknesses into a base, and he'll stack them up to a certain level. Then there will be a cover. To the immediate left here in this picture is a covered base into which are all these coils sitting. There will be an atmosphere added so that the coils don't tarnish. It will be heated up to a certain point, and because of the quantity of metal and the mass of the metal, it has to be heated for a certain period of time to allow it, every bit of that metal that's in that furnace, to relax, anneal to the right level. And then the furnace is opened. The other type of annealing is strip annealing, continuous strip annealing. This is on the fly annealing. Here you see an annealing line, and in many mills you have an annealing tower where the furnace, the strip has to be fairly thin to do this, but you can anneal it on the fly. And the annealing happens, say, in this highlighted area. There's no furnace around it. It's all atmospheric heated. And you come out and it's relaxed. Brass and copper are done this way many times. It's an expedient way of doing it. Gets things processed faster. Finishing operations, and what do you do after you roll all this stuff? Well, at the end of finishing, or at the end, you may need to clean things off the surface of the metals. During rolling, you have rolling lubricants. You may have developed and some of these lubricants, and usually it's a water-soluble oil, that has to be taken off in many cases because of the different oil than what you want to put on if you're packaging it with a special preservative. They can clash. There could be, and you want to make sure it doesn't have any oxides on it or anything like that. In finishing, you also slit it. You cut processed coils to width for the order. You provide the final length, width, length, and weight. Okay, you slit to width. Sometimes a mill or a manufacturer can only handle 100-pound coils, 200-pound coils, or their machines will only take a maximum 300-pound coil on the payoff. So you have to look at all that. And they may have specific packaging. Most everybody wants to use every pound that they get these days. So final packaging is very important to get those pounds that are produced, that are the right width, length, weight, and temper to the customer in pristine order. So you have a slitting operation. Slitting operation, here it is schematically. Here you have a wide sheet being slit into threes or thirds. But here's a close-up of a slitting operation where you have the metal being cut, but you have the knives, which are in crosshatch, coming from the bottom and the top. And you have to watch, because you're not cutting the metal, you're more like tearing it apart precisely. It's hard to explain. The surfaces are nicely done, but you end up with a burr unless the customer asks for the burr to be cleaned, which is another operation. They may ask for it to be packed burr up or burr down. So that has to be accommodated in how the coils are put together. Then you have the final materials stacked. You have spacers, you have protective cardboard, you have protective papers. The paper or packaging many times has vapor barrier or vapor corrosion inhibitors in it. This happens to be from Olin, but they do strip too. Here's some protected material and going to go into boxes. So let's talk about alloys. Copper alloys are designated by the UNS, a Unified Numbering System that was developed in 1974, or begun in 1974. It was developed prior to that over about a decade and a half of evaluation of what we could do, copper industry and other industries, metals industries, to number and name alloys in a better sequence and more identifiable way. Originally, there were only 3 numbers for an alloy, like 260 brass was 260. Now you have C, which is copper, means copper, plus 5 numbers. So it's 26000 for 260 brass. The extra 2 numbers many times allows modifications, small changes to be registered. And this includes both wrought and cast alloys. And CDA administers this system for copper. There's an overall UNS administrator that covers everything. Well, copper alloys have all kinds of different elements added to copper. Alloy 110 has nothing in it. It's just pure copper. But if you're looking at brass, you have zinc added, which is ZN, and it changes the color somewhat. Copper is a red color, one of the few metals that has color other than silver or gray. Zinc, when added progressively, turns copper into a yellow gold color. Nickel, when added, changes copper into a whitish, well, it starts with a small amount, it turns sort of pink, and then it turns sort of a golden color, and then it's white. About 15% you get pure white. Our coinage that you have in your pocket, nickels, dimes, quarters, half dollars, and dollars. The silver part is actually 75-25 copper nickel. Produced for the mint. So there's a whole series of elements that can be added to make the alloys. The wrought families are such. Pure coppers go up to about 150. 151 to 199 are age hardenable alloys. The copper zinc alloys brasses are the 20,000 series. The leaded brasses are 30, the 3s. C40XXX is copper zinc tin alloys, tin bronzes, sometimes called tin brasses. Then you got the 5 series, which are at the low end copper tin, which is traditional bronze. Ancient bronzes from Rome and Greece and so forth are tin bronzes. And you have some upper levels in that numbering area called tin bronzes with lead or phosphorus or others. And you have the 6s, you have copper aluminums and copper silicon. bronzes, different series of alloys. And the 7 series is copper nickels and copper nickel zincs, or nickel silvers. These are the copper nickel zinc alloys are all silver in color because of the nickel and the zinc. In the 800s, they're cast, 8 and 900s. Commercially pure copper are at the very low end. You have high coppers and copper zincs, or you can have them containing other things through the 800s, and other alloys in the 900s, the bronzes, aluminum bronzes, nickel aluminum bronzes, copper nickels, etc., etc. The most common copper alloy is alloy 110. Its composition is 99.9% pure, but it has no other listing for any other element. So essentially it's pure copper. Used for roofing, gutters, flashing, etc. Also is used for wiring and electrical goods. It's used in your circuit boards, in your computers. It's used for, and those are made out of a lot of times foil, which is 110. When you ask for copper, just copper, and have no spec, what you're going to get from somebody is usually going to be 110. Okay, you got all these different uses, a lot of electrical and electronic parts. In automotive, we used to list gaskets and radiators. Now it's mostly wiring and electronic parts. You have all kinds of different activities where these materials are used. Here's some examples. And I would note there's a distillation vat in the bottom of the picture. In the bottom left is a copper motor rotor that is infused with copper in the rotor. These are electrical industrial motors, very high efficiency. A version of said motor is used in Tesla motor cars. So it gets around. The most common copper alloy is 260 brass. It's the world's biggest used alloy. It's relatively inexpensive. It has a huge property range. It's easy to process, given the right parameters. Cartridge brass. It gets it. Brass fillings, and those are generally 260 brass. If you go into Grand Central Terminal, New York City, which was built in the early 1900s, there's brass railings there. Hardware, you got all kinds of pieces and parts that are made out of 260 brass. Here's some examples. Believe it or not, your electrical outlets and your electrical switches in your house have springs and parts like screws and so forth that are made out of 260 brass. They're not made out of just pure copper. These are generally like 0.32 thickness, so they're thick. But 260 brass is easily manufactured, easily recycled, and at that gauge, conductivity is good, and it makes reasonably good spring components because you got to plug things in and take them out, and plug things in and take them out. And your switches have to operate over multiple years. So 260 was selected. I asked somebody very specifically why they did that. And there you are. I don't know, how many minutes are we on? I say about 8 minutes or 7 minutes. If there are any questions.
Yes. Yes, once again, please submit your questions using the tab on your webinar toolbar.
Oh, that's good. I hope that was clear. I did make some modifications from earlier programs that I'd given maybe 7 or 8, 9 years ago. But the processing regime for these things is very similar from year to year, month to month, decade to decade. There have been some adjustments in processing. There's more processing of thinner materials. Oh. In any event, and there are more complex alloys being processed these days than ever before, simply because there's been a tremendous number of alloys that have and can be horizontal continuous cast and or batch cast in some way using specialized electric arc furnaces and so forth for unusual applications. These materials require special handling and special processing, but they are very valuable. Bearing materials and parts in automotive, aircraft, space. And I might note that we get a number of calls, a number of questions every year, every month concerning cryogenics, in other words, use of copper in cold applications. And unlike some other metals, which properties don't tend to be very good when it gets colder, copper is quite good. In fact, some of the conductivity is better at cold temperatures. So if you're sending a satellite out into orbit, or you're flying a jet aircraft, whether it be a fighter or a commercial jetliner, copper alloys perform very well. Did we have any questions?
We did not have any questions pop up. So thank you to Jim and to everyone for joining us this afternoon. Make sure to mark your calendars for Wednesday, December 5th for our end of the year webinar with ITR Economics. Until next time, please fill out your surveys and look for the recording. Thank you.